So in the last video, what we learned is if we have an equation in its standard form, we can come up with the parameterization of that equation fairly easily. However, there's infinitely many parameterizations that represent a curve in its standard form. And if you care about which parameterization you get, well then quickly things become a lot more difficult. But whether it's the easier example or the harder example, what we learned is how to go from the standard form to the parameterized form of an equation. In this video, what I want to do is talk about how to reverse that process. What if we started out with the parameterized equations of a curve? Maybe these ones that we just figured out, where x is equal to 6t minus 2 and y is equal to 3t plus 1. What if you wanted to come up with the standard form of this equation? I mean, one option, I guess, would be to plot some various t values, sketch the line, and then look at this line and figure out what its equation is. But there's got to be a quicker way. There's got to be an algebraic way of going from the parameterized form to the standard form. And it turns out there is, and it's fairly straightforward. All you have to do is eliminate that parameter t. You're like, what do you mean eliminate that parameter t? Well, I have two different equations, x and y. So what I can do is solve one of those equations for my parameter t. So maybe I'll take this first equation right here and solve it for t. I'd add 2 to both sides to get x plus 2 is equal to 6t, and then divide both sides by 6 to get that t is equal to x plus 2 divided by 6. Now that I have t solved for in terms of x, I can substitute that into this equation. So instead of saying y equals 3t plus 1, I can say y is equal to 3 times x plus 2 over 6 plus 1. I have two equations. I use one of them to solve for my parameter t. I substitute that in for t into the other equation to eliminate that parameter t. What I now have is an equation that gives me the y coordinate in terms of the x coordinate. You could stop right here, but you might as well simplify things a little bit. If I take this 3 and distribute it through the parentheses, I get y equals 3x plus 6 over 6 plus 1, which I could think of y equals 3x over 6 plus 6 over 6 plus 1, which I could think of as y equals 1/2 x plus 1 plus 1. In other words, y equals 1/2 x plus 2. Wait, 1/2 x plus 2, I know what that looks like. It's a straight line with a slope of 1/2 and a y-intercept of 2. Yeah, that's exactly what we came up with in red here, right? Here's the y-intercept of 2, and the slope is 1/2, meaning you go up 1 each time you go right 2. Going from the parameterized form of the equation to the standard form, algebraically, is as easy as just solving one of the equations for the parameter and plugging that into the other equation. Note that in this specific case, I solved the x equation for t and plugged that into the y equation. But there's no reason I couldn't have done it in the other order. I could have solved this equation for t, so get y minus 1 equals 3t, and then divide both sides by 3 to get t is equal to y minus 1 over 3. And now, since it's the y equation that I chose to solve for t, it'll be the x equation that I plugged that into. So x was equal to 6t minus 2, but instead of writing 6t minus 2, I could write 6 times y minus 1 over 3 minus 2. I can simplify this mess a little bit. Let's see, this 6 and this 3 cancel out, and I'm left with 2 times y minus 1 minus 2. I can get rid of these parentheses by distributing the 2 to get x equals 2y minus 2 minus 2, or x equals 2y minus 4. You're like, whoa, it's a different equation. No, it's not. It's just in a different form. If I solve this equation for y, maybe add 4 to both sides, and I get x plus 4 equals 2y, and then divide both sides by 2, I get y equals x plus 4 over 2. In other words, x over 2 plus 4 over 2. In other words, 1/2 x plus 2, the same thing that I got over here. The takeaway is, when you have two equations, you get to pick which one you want to solve for your parameter t, and then substitute it into the other one. However, sometimes you can save yourself a little bit of extra work by being clever in terms of which equation you solve for t. In this case here, I wanted to end up with the standard form. The standard form has the y solved for. So if I want to end up with the y solved for, it makes more sense to solve the x equation for my parameter t. Because if I solve my x equation for the parameter t, that leaves the y equation as the one I'm going to plug in the parameter for, which will leave me with y already solved for. Note that over here, when I solved the y equation for t, I ended up with an equation that had x all by itself instead of y all by itself, which is fine, But if your goal is to get y all by itself, you have to do some extra work at the end if you do the problem this way. So maybe you're like, okay, so you're telling me that I'm always going to solve the x equation for t and then plug that into the y equation? Well, no, not necessarily. You're always going to do that if your goal is to end up getting y all by itself. But sometimes you'll get parameterized equations that don't lend themselves very well to standard form. What am I talking about? Imagine if you tried to solve this equation for t. Maybe first you'd subtract 1 from both sides to get x minus 1 equals 3t squared, and then you divide both sides by 3 to get t squared is equal to x minus 1 over 3. Then you take the square root of both sides of the equation, and that's where you get into trouble, because when you take the square root of both sides of the equation, you got to put in the plus or minus. So I get t is plus or minus x minus 1 over 3. But that's problematic. With this plus or minus in here, I'm going to get into trouble. Because how am I going to plug that into the other equation? I'm going to end up with y equals something plus or minus something, which I can't have in my standard form. In my standard form, I have to have exactly one value of y for each value of x. But because of this plus or minus, that won't happen. What do you do in cases like this? The short answer is it's not a big deal. Because of the square on my parameter t here, it doesn't work out well to solve this top equation for t, which is what I need to do if I want to plug into this bottom equation to end up with y all by itself. But that's fine, you don't always have to have y all by itself. I can solve this bottom equation for t. I'd get y plus 4 is equal to t cubed, and therefore t is equal to the cubed root of y plus 4. Because this exponent is an odd number instead of an even number, when I take the cubed root, I don't have to put in the plus or minus out in front. That's good news. I can write t in terms of y without a plus or minus, so now I can plug that into my other equation. I had x was equal to 3t squared plus 1, but t is equal to the cubed root of y plus 4. So x is equal to 3 times the cubed root of y plus 4 squared plus 1. I've eliminated my parameter t. I've changed these two equations into one single equation. It's just that single equation isn't solved for y, it's solved for x. And that's totally fine. Y is not a function of x here, which happens all the time with parameterization because having two equations kind of gives you this extra power. In the case where y is a function of x, generally you want to solve for the y. But when y is not a function of x, no big deal. Just come up with an equation that relates together the x's and the y's. The big takeaway here is when you can't solve the equation that gives you x as a function of t for that parameter t, you won't be able to write y as a function of x. But that's totally fine. Instead, just take your other variable and solve that for t and plug it into your x equation, and that'll leave you some equation relating together the x's and the y's, which is sort of as good as you can do in this case. If you have the parameterized form and you want the standard form, it's as easy as just substitution. Solve one of your equations for the parameter, plug it into the other equation. As long as both of your parameterized equations are really simple, that will always work and you'll have lots of freedom. Sometimes you'll see cases where the equations are a little bit more complicated, but really that's not that big of a deal. Just take the one that you can solve for t and solve that one for t. That's how you go from parameterized form to standard form.